Hello, my name is Hugo Aranberri, and I am here to present this talk entitled New Types of Antiferroelectricity. This talk is part of the ISAF2021 conference, and the work here presented has been carried out at the Luxembourg Institute of Science and Technology in collaboration with Natalia Fedorova and under supervision of Jorge Iñiguez. And the funding comes from the Fonds National de la Recherche of Luxembourg. Okay, so let's start by defining what is an antiferroelectric. A textbook or Kittel-like antiferroelectric has to fulfill two conditions. First, it needs to show an antipolar pattern of electric dipoles so that the overall dipole is zero. And second, it has to arrive to a polar state when subject to an external electric field. So antiferroelectrics have been proposed for several applications, among which one of the most promising is for high-density energy storage. Now, the main challenge in the field is that antiferroelectrics are still relatively scarce. So in our group, we started to look for new antiferroelectrics. This talk will have two parts corresponding to two new different types of antiferroelectricity that we have predicted. In this first part, I will tell you how a high-throughput first principles quest led us to identify antiferroelectricity in three oxides. So we studied the instabilities of the cubic perovskite phase of several non-magnetic compounds, looking for strong antipolar instabilities. Now, the only compound in which we did find a leading antipolar instability was cesium vanadate. We tried to find the ground state of this compound starting from a perovskite phase, but the process of condensing the strongest instability, relaxing the structure, and finding the new instabilities became very long and tedious. So this probably was because the instabilities of the cubic perovskite phase are very strong, and that means that the cubic perovskite phase is not a good reference structure in this case. Nevertheless, with the help of first principles molecular dynamics calculations, we did manage to find the ground state of cesium vanadate. And we found that the ground state structure is shared with potassium vanadate and rubidium vanadate, and it looks as follows. So in the figure, the black atoms correspond to potassium or rubidium or cesium, the green atoms to vanadium, and the blue atoms to oxygen. The oxygens surrounding the vanadium cation form tetrahedra, and these tetrahedra share two corners with other tetrahedra, forming infinite zigzag chains. Now the structure is very similar to the pyroxene structure, which is one of the most abundant mineral families on Earth. We found experimental articles dating from the 1950s describing this structure for our three vanadates. So next, we realized that the tetrahedra that form these pyroxene-like oxides are not platonic. And since they are not perfectly symmetric, this center of negative charge does not coincide with the center of positive charge, so that each one of these tetrahedra carries an electric dipole. Now if we look at one of the chains, we see that within each chain, the in-plane component of the dipoles is antiparallel, while the out-of-plane component is constant along the chain. Now looking at the full structure, we see that, as in the case of pyroxenes, neighboring chains have their apical oxygens pointing in opposite directions. So if we draw the dipoles on top, we can see that the out-of-plane component of the dipoles forms an antipolar pattern of dipoles. So we can claim that the system is antipolar, but in order to classify it as antiferroelectric, the system has to be able to reach a polar state under an electric field. We identified a possible polar state to which the system can switch to by rotating every other chain. We found that this configuration is metastable in potassium vanadate and the other vanadates, and in this structure the out-of-plane dipoles are parallel for all the system. Okay, so having found this, we use a technique called nudged elastic band to compute from first principles the switching path between the antipolar and the polar states. So now I'm going to play a movie showing how the crystal structure evolves when going from the antipolar ground state to the polar state. Now on the right here, you will see the evolution of the energy on top and on the in-plane and out-of-plane polarization on the bottom. So you see that the switching occurs in two steps. In the first step, only half of the tetrahedra of the rotating chain switch, and in the second step, it is the other half of the tetrahedra that complete the switching. Now, with the energy profile obtained from the switching path, we can build an approximate electric enthalpy like the one on the bottom left in this slide. And by giving values to the electric field and keeping track of the enthalpy minima, we can reconstruct an estimated hysteresis diagram. We see that at room temperature, it features the double loop that is characteristic of antiferroelectrics, but unfortunately, the estimated switching fields is close to 40 megavolts per centimeter, which is way too large for practical applications. Okay, so let me wrap up this part. We have predicted that potassium vanadate along with other vanadates is antiferroelectric, and we have computed the switching path, finding that the switching field is too large. We are now simulating mixtures of potassium vanadate and potassium niobate, and our preliminary results indicate that this kind of substitution significantly reduces the switching field. And very importantly, we find that the key structural feature that enables antiferroelectricity in these compounds is shared by many other mineral families, including the all-important family of pyroxenes. So our findings suggest that there may be many antiferroelectrics in disguise out there. You can see more videos and read more about this work in the article shown in the black box down there. Okay, so in the second part of the talk, I will tell you how to create artificial antiferroelectrics from ferroelectric superlattices. So when you have a ferroelectric system like lead titanate surrounded by a paraelectric system like strontium titanate, a competition arises between the polar distortion and the electrostatic penalty imposed by a paraelectric. This competition can result in the ferroelectric breaking into domains with opposite polarization, so that in this way the polar distortion is developed while the electrostatic penalty is minimized. Such a behavior has been recently observed experimentally in lead titanate strontium titanate superlattices and was predicted by first principles calculations some years ago. In this work, we study these structures by means of second principles calculations. So let me very briefly introduce to you what do I mean by second principles calculations. In the second principles framework, the model potential of a material is expressed as a Taylor expansion around a reference structure in terms of atomic displacements and lattice distortions. So the tensors kappa and lambda, highlighted in blue in the slide, are fitted to first principles data once and only once for each material. And the resulting model can then be used for atomistic simulations like Monte Carlo calculations or molecular dynamics, and allow you to compute larger systems than DFT with atomistic precision and moderate computational cost. Okay, so this framework is implemented in the scale-up code, which is described in detail in the references shown in this slide. And the second principle superlattice models that we employ in this work were developed in the group a few years ago, and you can see on the right that they predict very similar outcomes as first principles on the real experiment. In fact, these second principles models have been used in previous works like the one referenced here at the bottom right. Okay, so let's start by analyzing the ground state of a 3 lead titanate, 3 strontium titanate superlattice at 0 Kelvin. Now in the figure, I am showing the dipole pattern of the ground state we did find. And the upper half corresponds to the lead titanate layer and the lower half to strontium titanate. You can see that the dipoles in PTO form an antipolar structure in which the domain walls show no polarization along Z. And on the STO side, the resulting dipoles are very small and negligible. Okay, so we have our antipolar ground state, and in order to verify that this system behaves as an antiferroelectric, we have to test if it can reach a polar state when subject to an electric field. So for this, we used Monte Carlo simulations under field to simulate the hysteresis diagram of this system. And by monitoring the out-of-plane polarization under an electric field cycle, we see that the system presents an antiferroelectric-like hysteresis loop. At large fields, we also see that the system has fully switched to a completely polar state. So therefore, we can say that PTO-STO superlattices display an antiferroelectric-like behavior. Now on the right side, you can see the result of a similar Monte Carlo-based simulation, but this time at room temperature. If we look at snapshots of the system at 0 applied field, we can distinguish an antipolar order. And similar snapshots at large fields reveal a polar order in the system. So since we are interested in practical applications, all the results I will show from now on will be at room temperature. Now, having computed the hysteresis diagram, we can use it to calculate the stored energy density as a function of the maximum applied electric field, which I am displaying at the bottom. Now, since the system shows no hysteresis, the stored energy density is proportional to the integral of the PE curve over the y-axis. And we find that for a maximum field of 3.5 megavolts per centimeter, the system can store up to 50 joules per centimeter cube. Also, because there is no hysteresis, the estimated efficiency for this cycle is of 100%. So to put this number in perspective, at this field, the best antiferroelectric can store up to 150 joules per centimeter cube with an efficiency above 90%. But other well-known antiferroelectrics can store a similar amount of energy to our 3PTO, 3STO superlattice, although with a much lower efficiency. But of course, this was just the first superlattice we studied. Can we improve this figure by varying the design parameters? The first thing we looked at was the effect of biaxial compressive strain on the antiferroelectric performance. Here in the top row, you can see the polarization electric field curves for increasing compressive in-plane strain going up to 3%. So compressive strain favors the polar distortion in lead titanate, and therefore the saturation polarization increases, and this results in a larger stored density. Also, for the largest strain considered, the initial slope in the PE curve is reduced, which is the perfect scenario for an increase in the stored energy density. And remember that we want to maximize the area to the left of the curve. So for the 3-3 superlattice, applying 3% compressive strain makes the stored energy density go up to 60 joules per centimeter cube. And we did find that when studying the combined effect of strain and other design parameters, applying a 3% compressive strain yielded a consistent improvement in the stored energy density. So from now on, all the results I will show will be for 3% compressive strain. Next, we studied the effect of varying the thickness of STO and the PTO layers themselves. On the top figure, you can see the different PE curves for varying PTO thickness, and you see that having more PTO layers increases the saturation polarization, which in turn increases the stored energy density. But however, there is this other effect that increasing the PTO thickness also reduces the switching field, which can result in a decrease of the stored energy density depending on the magnitude of your applied field. So therefore, there is a trade-off between these two effects, and it is not clear a priori how to maximize the stored energy density. Similar arguments can be applied for the STO layer, since you can see in the figures that the effect of increasing the STO thickness is very similar to that of decreasing the PTO thickness. So we ran many calculations with varying thicknesses to find the optimal performance. And here you can see the result for a maximum applied field of 3.5 megavolts per centimeter. And in the horizontal axis, you have the number of STO layers, and in the vertical axis, the number of PTO layers. Now, the color code corresponds to the stored energy density, being red the highest. We see that the optimal region is that close to an equal amount of PTO and STO, but with slightly thicker STO. In this table now, you can see that, for example, the 4 PTO, 8 STO superlattice, in that superlattice, the energy density at 3.5 megavolts per centimeter goes up to 70 joules per centimeter cube. Okay, so let me wrap up this second part. We have found that ferroelectric paraelectric superlattices present an antiferroelectric-like behavior that might be useful for energy storage applications. We have optimized the room temperature energy density with respect to strain and layer thickness. We predict that these systems can store more than 70 joules per centimeter cube with 100% efficiency for a maximum applied field of 3.5 megavolts per centimeter, which is competitive with other known antiferroelectrics. We are currently working on further optimizing the performance of these superlattices by doping STO. Our preliminary results indicate that a significant enhancement can be achieved in this way, and we have already found configurations for which more than 100 joules per centimeter cube can be stored. We are currently working on writing a manuscript about these findings. With this, I thank you for your attention.